All right, so today we're going to talk about something a little bit to do with software design. But this is some overlap between software design and algorithm design as well. So we want to talk a little bit about it. So let me just give you some context about why we are talking about this. So from the lecture yesterday on Wednesday, so we spoke about this Dijkstra algorithm. So we kind of focus on just the mechanical part about how the algorithm should be understood and also how we can apply the algorithm to trace, about how you can figure out the shortest path of every other vertex to the source vertex. That's what we did yesterday, right? Eventually, which we'll do starting from next week, Monday, we'll try to see how we can argue about the correctness of this algorithm. We just don't want to do testing, right? Testing in some way has its limitation. We want to do something that's rigorous and also mathematical to show that for any given graph, we are able to show that the Dijkstra algorithm always going to work. Of course, to really do it thoroughly, we have to apply mathematical induction. That's something I'll give you some exercise to try it out for assignment number 3. But I'm going to also give you enough background also in the lecture next week. But now, in order to really prove this, we need to learn something called loop invariance. Okay? You may have heard about the term before, but that's okay. I assume everybody might be just new to this. So we're going to see exactly how we can understand about loop invariant today. Not exactly Dijkstra. That might be a little bit too complicated to understand to begin with. Today, I want to give you some mini lecture, hopefully no more than halfway of the session, just to tell you about precondition, postcondition, and also loop invariant by some very simple, a little bit contrived example, just for you to understand how to understand loop invariant mechanically and with a little bit tracing as well. Hopefully that will be thorough. And then after the break, we can talk about some exercise, which I already put on the lecture site about the tutorial. We'll see how much we can go for the exercise after the break. If we're able to finish it, that's great. If not, I will carry on. Sometime, maybe next week in the tutorial or in the lecture. Right, we'll see how that goes. Okay. All right, so this is something we're going to start with about correctness of loops. So we got to learn about loop invariant. But just before that, you can also see the corresponding slides as well. So this will be slide number 62. Okay, that's where the topics will start. So we are making some assumption about the syntax. So since we're talking about iterative algorithm, just like a Dijkstra algorithm, so we're just using the while loop syntax. But of course, while loop and for loop, they're basically just different syntax for the same idea. You can think about, once we learn about the idea for the while loop, you can easily translate any for loop into while loop and do the corresponding arguments. That's actually possible, right? But let's focus on while loop for today. I just want to go a little bit, so a few bullet points, and then we'll switch to iPad and work through the ideas. Okay. Okay, so typically, if you program in any languages like a C or Java or Python, they don't really have the built-in loop invariant construct. So you can think about loop invariant is more at the design level, but that's definitely some concept you have to learn in order for you to devise the correct algorithm. So what we're going to do is we're going to somehow extend what we have already in Java conceptually by some assertion. You can think about assertion, you like a JUnit assert true. We're going to say at a certain point at the program execution flow, we're going to assert, for example, if the precondition is true or if the loop invariant is true, we're going to see exactly when to check them. So that also helps you understand exactly what loop invariant is about. Okay, and just for your knowledge, okay. So I'm going to learn about loop invariants over here, and in the community, usually people say when you can actually use a loop invariant to establish so-called partial correctness, in the sense that we don't really talk about whether or not your loop is going to terminate, right? So we simply assume your loop is going to terminate because it got very clear, like an exit condition and also like a loop counter, etc. That's something we don't really cover in this course. If later you really want to show that the iterative algorithm is going to terminate, make sure it doesn't really run forever, is something you have to prove separately. So in the more advanced level, like software engineering courses, maybe 4315, mission critical system, usually this will be covered in more depth. But for this course, we're not going to go that far. Let's focus on just the loop invariance. Okay, that's what we'll do. And just understand that we're only doing partially about the correctness. We are not really proving formally about termination. Okay, so that's about what I want to say, just in general. And let's now work on understanding about the syntax, right? That's something you will see in the tutorial exercise as well. let's start with this part here, right? So just look at this part over here, okay? So overall, you can see as part of the algorithm, we have some while loop, right? So here, so this is some syntax for iterative algorithm, okay? Let's write it down. So this part over here is called something for iterative algorithm. Okay, because we've got a while loop. And then you will see the capital S over here and over here. So S over here simply denotes programming statements. It can be arbitrarily complicated. It can be if statements, it can be just another loop, or just variable assignments. So think about the S over here is simply about programming statements. And we got something that's to be done before the loop is ever executed. And also we do another one, which will be the body of the loop, which is going to be executed every time we decide if there should be another iteration of the loop. So we got two kinds of programming statement, all right? And then this part here, of course, will be very critical because that one there will be a Boolean value, okay? So B here, right? So this one here, so this is so-called the state condition. Condition for us to stay in the loop. Let's just cover some basics, right? And then we'll get to how to check it, okay? So basically we're saying that as long as B holds to be true, you want to execute the body of the loop another time. The body for another iteration. Okay? You can try to think about the other way. As soon as B falls to hold, as soon as B actually stops to hold, which means it becomes false, that means it's now time for you to exit from the loop. So I can say as soon as B becomes false, exit from the loop, meaning that there'll be no further iteration that is possible for the algorithm to keep going. Okay. And then let's just see also this part here about inits. Okay, so let me use another color here. So this part here. So this is just about initialization, just for us to prepare before the loop ever starts. So this part here is just initialization. Or think about we are doing some prep for iterations. Okay. So that's about the algorithm usually we have. And let's now see that before and after. You will see that we got Q over here, and also we got R over here. Both of them will be some Boolean expression, something you can evaluate to be either true or false, right? Q and R, right? And we say that Q is something you check even before you apply the algorithm. Q is called a precondition. So this will be the precondition. And we'll give you an example in just one moment. And precondition is just to make sure the input is valid. Let's say, for example, if you want to perform a binary search on an array, you got to make sure the precondition is the array is sorted, right? Before you can do binary search. That's a precondition, right? If the precondition is not even satisfied, you don't even bother to go on. You might just throw some exception or signal some violation. At the end of the algorithm, right, let's say the loop actually exit. So this is something we want to make sure it is established. It's called postcondition, right here. So this one here is called postcondition. We're going to see example when we do the exercise today. But postcondition in general is more like, it's a Boolean expression, but it's actually going to relate between the input and output. It's more like an input and output relation. Okay, that's something we'll see, just in general. What's the relationship between the input and output that should be holding when the algorithm actually finishes? All right, so that's about the normal syntax we know. Okay, and let's now make it more mechanical. Okay, so going to look at this one here together with some flowchart. So we're going to see exactly how things will be executed along the way, and we're going to do exercises together. Okay. We're going to introduce something called loop invariance. Okay, loop invariant over here. And if you just look at the syntax, there are two places the loop invariant will be checked. So you can see assert I right here. Okay, let me just put it here. The I here is the loop invariance. By the way, if you look at the word invariant, literally, it should be a condition that should stay true all the time. On the other hand, if you look at something called loop variance, which is kind of beyond the scope for this course, when you talk about loop variance, it should be some value that should change all the time. But it's not the case for loop invariant. It should stay the same always. It should stay true, basically. Right? So there are two places we should check the loop invariance. We should check the loop invariance right before we may run the loop for the very first time, for the very first iteration. And then at the end of each iteration, we want to make sure the loop invariant maintained to be true. So there are two places, conceptually, we're going to check it. Right? So let's look at them. Okay? So for this one here, we want to make sure the loop invariant is established for the very first time. Think about it more like a mathematical induction. We want to make sure the base cases in the small input value will be satisfied. Okay? And then the second place, at the end of each iteration, we want to make sure the loop invariant is preserved. So we are able to go on to the next iteration without violating it. Okay? We still have the precondition and postcondition right here. Right? That's a precondition, and that is the postcondition. Right? Let's just remind ourselves quickly. So this is the precondition, and that one is the postcondition. Okay, and then loop invariant is checked in two places. Okay, so this is kind of the structure you will see usually for if I give you some questions regarding this concept. But let's look at the flow chart to understand it. Right, it's not difficult. Okay, let's take a look. Let's talk about like a normal correct path. You will hope your algorithm should be in such a way. The precondition on the input should be satisfied. And then you try to execute something in the beginning, and then the loop invariant should be satisfied. And then you go ahead to evaluate to see whether you should really go for the first iteration. And then you execute, let's say, for the first iteration. At the end of it, you want to make sure the loop invariant is maintained. And this kind of pattern here is going to go on for as many times as necessary, depending on how many iterations you're going to go for the algorithm. At the end of the algorithm, meaning that this condition here becomes false. In that way, we've got to make sure the post condition should be established as well. All right, so that's kind of correct path. But let's look at that in the diagram. Okay, let's look at that. Let's start with this. First of all, we want to make sure the precondition is satisfied. And then we're going to execute the initialization part for the loop. And then we're going to make sure for the first time the loop invariance is established, even before we get to any iteration. Okay? So this part here is really about the loop invariance established. Okay? If it is established, this part here is about the loop itself. Okay? I will just highlight it. Okay? you can think about this part here is really just about a loop. So now what's the logic for the loop? If this condition here for the while is actually true, that means I should go for another iteration by executing the body of the loop one more time, right? So let's say if that's the case, and I'm just going to make sure, so B is true, as long as it's true, I'm going to execute the body of the loop for one more time. And then I'm going to execute it right here. Now, comes the critical part. Let's say after I have done the current iteration, at the end of it, I want to make sure, before the very first iteration, the looping variant has been established. I want to make sure the body of my loop does not violate it after the first iteration. So that's why I have to make sure before, while I go back to checking to see if B is true again for another iteration, I want to make sure looping variance is actually still true, it's maintained. All right, that's an important step. Okay, I'll highlight it. So that one there, we go to the I here. So this is to say the looping variance has been maintained so far or preserved. Okay, of course, you can go for as many iterations you like as long as the B is true. Just make sure every iteration at the end, you got to make sure looping variant is maintained. All right. Now, let's say after the very last iteration, after I executed the body of the loop for the very last time, and then I still have to make sure the looping variant is still maintained after the last iteration. And now the B here is going to become false. I don't go for another iteration. So instead, I'm going to go for this path. I got to make sure the B here is not true. At the same time, the post condition must be established. That will be the end of the algorithm. Okay. So for that part, I got to make sure this post condition here is actually satisfied. At the same time, the condition for the while loop is actually false. That means I already exit from the loop, right? So what I have highlighted so far about this, and this. So that would be more like a correct path without any violation, right? So I think it's still kind of consistent with your understanding about the loop. The only addition is about the looping variance. You got to make sure it's established and also maintained. Okay, guys, any questions so far? All right. Of course, things might go wrong at certain points. So we might get either a violation for the precondition, for post-condition, or for looping variance. Let's see how things might get diverted into the wrong path, which is possible, right? You ought to be able to judge. Let's take a look. So here, if initially I'm checking to see if the input is legitimate, if the input condition, precondition is simply not the case, I got precondition violation. That one's obvious, right? So for example, if I check to see if my binary search array is simply not sorted, in that case, I got a precondition violation, all right? So that'll be the first kind you will get, okay? Precondition violation. Usually, it will be because illegal input. Okay, depending on how many input values you're taking. All right, let's look at the post condition first, and then we'll talk about looping variance. All right, so for post condition, it is saying at this point over here, B here is no longer true. That means no more iteration to go. In that case, I will get not B. But at the same time, I exit from the loop, but the post condition at this point is also false. That's not acceptable, right? So I'll get a post condition violation. Okay. So this part here will be post condition violation, right? So think about this will be unexpected output. Right? So precondition violation, post-condition violation. And for looping variance, right? Since we say we have to check it in two places, if either place actually failed, if the looping variant evaluated false, you're going to get a violation, right? Either because before the loop, after the initialization, if the looping variant simply evaluated to false, I got looping variant right away, right? It is not established. So this part here is about looping variant not established. Looping variants not established. Or another place would be, at the end of the current iteration, I try to evaluate I. However, I is simply evaluated to false. In that way, I got a violation right away. So for example, let's say you got an array of, let's say 10 elements. It could be that maybe in the 5th iteration, the looping variant is already violated. Then you just get distracted, right? You should really get disrupted right away for the execution flow. So this part here is going to be about the looping variants not maintained. All right. Any questions so far just about the syntax and also the flow? Right? We're going to see some concrete example for sure, but it's important to really understand about the different scenario that might fail, especially for looping variants, and also, see the new addition. All right? Any questions? Diego, you okay? Which part you might be confused? Tell me.
Just a little bit about the post-condition violation.
Sure.
Before entering the loop. Is that
Okay. No. Think about post-condition. Oh, it's not. Okay. Let's say at this point. Yeah. Okay, very good. Let's clarify that. At this point here, we're deciding whether or not there should be another iteration for the loop. Oh. So we are trying to evaluate if B is true. Yes, we go for another iteration. If B is already false, that means we exit from the loop. Right. In that way, we're gonna, as soon as we exit from the loop, we gotta check for post-condition. Mm-hmm. Okay. It's good you ask, but let me write it down. Okay. So when you say not B means exit from the loop. Okay, good. All right, guys, any other clarification needed? Yeah, go ahead.
So like the first case where you go to the loop period violation,
yeah.
how would that happen as soon as the loop starts? Because it goes straight from initialization to like looping period.
Mm-hmm.
It doesn't go through the spawn.
Good. Okay, that's a good question here. So I think your main concern is about this part over here, right? Okay, sure, let's talk about it. Okay. First of all, you're right. This part here is the actual loop. Conceptually, there should be some preparation that's to be done before the loop ever starts. And then we're saying that should be the job for sinit. You got to do some preparation. So we're saying, you think about mathematical induction. If you don't check for this particular violation, it will be as if you have some mathematical induction proof without the base cases. It's really like that. You want to make sure the looping variance, even before the loop starts, is already true. And we want to make sure all the subsequent iterations are going to maintain it, including the last iteration. So when we exit from the loop, we know that looping variant is true, and also exit condition is actually true. I mean, B is not, is actually false, and post condition should be true, right? Yeah. All right, okay, let's go with this. And then on Monday, I'm also got another diagram to show to you the more intuitive view about everything together. But let's do things a little bit mechanical, just to trace, okay? All right, let's now take a look at one example. Oh, question? Oh, okay, just want to be sure. Okay, let's take a look at this. Guys, it's very contrived, I would say it's very explicit. I think that's exactly the point, to really do this, and it will do something a little bit more interesting after this, okay? Okay, let's take a look at this. So this one got everything we just said, right? Let me clarify that. Okay, let's take a look at this, okay? I'll get to the diagram in a moment. So this one here would be the precondition. We check first. We want to make sure before we execute this algorithm, the variable here, just I, should be equal to 1. Okay, that's precondition. And then we got looping variance right here, and repeated by itself here. We want to make sure it is established and it's also maintained. Okay, looping variance. And then we got the exit, the state condition here. Okay. So this is the B that we spoke about earlier. Another point you can make. As soon as not the case, I less than or equal to 5 is the case, we're going to exit, right? You can keep that in mind. We'll see that, okay? And then, so this part here is the only line for the body of the loop. You can think about this part here is simply the statements for the body of the loop. By the way, for this particular example, I don't have any init, but that's okay, right? You don't really need to have that always, okay? And then, finally, upon the exit from the loop, we got post condition right here. You can see all the things we talk about, they're simply Boolean condition. Okay? And one more thing to mention, and we can do a little bit of tracing for you to get more idea. Okay? So all the things we talk about, so we got precondition, post condition, and we got loop invariance. So these are so-called contracts for your algorithm. So there is a very sound software engineering principle called design by contracts. Again, beyond the scope for this course, right? Maybe in your 3311, your professor will actually talk about design by contracts. But it's really about every time you want to design your methods, function, algorithm, make sure you think about what's the precondition, what's the postcondition, and if you're going to implement it iteratively, what's the loop invariance? So these are the things you want to keep in mind, right? It's called design by contracts. Okay, I'll just mention the name. Design by contracts, okay, or DBC. Okay, you'll see that quite a lot when people talk about software design. Okay, all right. Let's now, given this, let's now trace it. Right. All right. The flow I already went over with you in detail in the previous page. Let's go ahead and trace it like a normal. And I'm going to draw a tracing table for us. And just for convenience, let me put it explicitly. The loop invariance that we're talking about would be just this one. Let me just repeat it. It would be basically 1 less than or equal to I, and then less than or equal to 6. Okay, so that's the loop invariance. Just keep that in mind. And then we're going to look at how we can trace it. Okay, this column here, we talk about iteration number. And then there's only one variable that we are manipulating, which is I. And then we want to know whether loop invariance is at the moment holding true. Right? And then we're also going to look at whether or not the state condition B is true or false. Okay? And of course, in this case, B here will be I less than or equal to 5, right here. And the final column, we want to see whether or not the post condition is actually established. That one there, you can see is I equals 6. I equals 6. Right, of course, depending on what you're given, the condition might be different, but always Boolean condition. Okay. Let's just trace it. Could be a little bit boring, but let's get it done. Just make sure we understand exactly the point, and then we can do more interesting exercise after the break. Okay. Let's say initialization. The only thing we can assume, there's no initialization part for here, right? But we only know that in order for you to get to this point, the precondition must be true. That means I must be equal to 1. Otherwise, we would have got precondition violation. So in that case, I should be just 1. Okay? And then at this point, when we try to evaluate I equals 1, and to see if the loop invariant is established. Is it? It is, because 1 is indeed between 1 and 6. Okay? So this one here, yes. So we say that the loop invariant is established. right? So the 1 here will satisfy this loop invariance. Okay, true. And 1 here less than or equal to 5, true. That means go for the first iteration. So we're going to go for also true. Okay? And what about post condition? You don't care. You only care about evaluating the post condition once you exit from the loop. At this point, we don't care. Okay? Don't care. We don't even bother to evaluate. Doesn't matter if that's true or false. Doesn't matter. All right? Quick question. Let's say I move on with the first iteration and so on. How many iterations do we have in total? Should be an easy one for you, right? Go ahead if you got an answer. Yeah. How many? Yeah.
No, sorry,
please. Yeah.
Say 5, including the initialization.
Well, actually, we don't include the initialization as part of. Yeah. So you mean 5, right?
Yeah.
I agree. Exactly. Good. Okay. It's gonna be 5, but let's double check, right? Yeah, by the way, yeah, as your fellow student pointed out, initialization definitely is not included as part of the iteration. No, it's only preparation. Okay. I'll go a little bit quick, right? So because this part here is not really that hard, okay? So we're gonna get, I'll try to be systematic here. So we got exactly 5 iterations, yes. Iteration number 1, 2, 3, 4, and 5. The last iteration. Okay, let's now take a look. What's gonna happen, okay? For the first iteration, at the end, we're going to increment the value of I just by 1, okay? So that means it's gonna be incremented to 2, okay? And then, now we're going to check whether or not the loop invariance is maintained after I has been incremented from 1 to 2, right? In this case, yes. 2 is still between 1 and 6. Maintained. And then we kind of go back to the while condition here. So now 2 is still less than or equal to 5, right? So we go for another iteration. Okay, and for post condition, we don't care. Let's do one more, and then we'll see the result. Let's just do one more, okay? So now for the second iteration, we're back here. We're still going to increment further I by another 1. So that means it's going to be incremented from 2 to 3. And then after that, we're going to check to see if 3 is going to satisfy the invariance, if that's maintained. So now you can see that 3 is still between 1 and 6. So indeed, it is maintained. And then if we check to see if 3 right now should be worth another iteration, yeah, 3 less than or equal to 5, yes, that's true. So go for another iteration, right, and etc. Okay. Are we okay so far? Are you guys lost in any place right here? Just tracing, right? Just remember, you check the loop invariance, first of all, after the initialization, and then at the end of every iteration. That's the principle, right? That's a little bit more mechanical definition, but we should also learn about the more intuitive side, which I'll cover in the lecture on Monday, okay? All right, let's now fill out the table, okay? So if you go on and do it, you can double check. And then from 3 to 4, 4 to 5, 5 to 6, okay? And then you will see that this will be maintained, this will be maintained. And after the last iteration, this will be the last iteration. Loop invariant still maintained. When we exit. Because when I is equal to 6, 6 less than or equal to 5, false. Time to exit, okay? So in that way, we're going to see the state condition here is false. So that means we're going to exit, all right? In all the previous iteration here, we don't care about post condition. Now, this is the only place we have to care because now the loop is already exited, so now let's now check the post condition. Right? So you can see that 6 over here equal to 6. Wow, satisfied. Right? This one here will be this. Okay, let me make a little bit of notes here. At this point over here, we know that the looping variance is maintained, and also the state condition is not the case. That's why we exit. And also the post condition right here is also satisfied. In the final states, these are the 3 conditions we will hope that will be satisfied. That's how we define correctness for your iterative algorithm in general. Right? Any questions about this? We'll do one more tracing today, but in a slightly more interesting example, slightly. Okay? But this one here, just to make sure you get the initial concept understood. Okay? All right, one more thing before we take a short break. Right? All these are good. And then we want to make some final conclusion to say this algorithm here is actually important. Sorry, not important. It's actually correct. Okay? So the way we define correctness is based on the contracts. Okay? I'll write it down. So correctness is with respect to the contracts that we have specified for the algorithm. Meaning we got precondition, we got postcondition, and also looping variance. Okay, let me give you the general criterion. Okay, correctness. Okay, let me put it here. Right here. So in general, if you want to show that your algorithm is actually correct, okay, first of all, you want to make sure you already exit from the loop. And you want to make sure your looping variant has been maintained ever since it's established, never violated. It's maintained since established. And then the final one is you want to make sure these two together will imply, logically, that the post condition is actually established. Okay, I'll apply this into the example we're doing here. So this will be the post condition. Okay, so now how do we apply this example here to this general formula? Okay, first of all, let's now highlight it, and then we'll do the specific example. Okay, let's take a look. So for our particular example, not the case, this condition means we exit. So we have not the case, I less than or equal to 5. Okay? And the looping variants have been maintained ever since it's established. So we got 1 less than or equal to I less than or equal to 6. Okay? And now, does that imply the post condition right here, which is I equals 6. This is what we call a proof obligation. It's an obligation for you as a developer to discharge or to show before you can claim that your algorithm is actually correct. So that's what we call proof obligation. Okay? Proof obligation. All right, for this one here, let's talk about this, even though it's simple. How do you show that this is the case? If you got, for example here, not the case, I less than or equal to 5. That's equivalent to I strictly larger than 5. Agree? Right? Just negate it. And then, if you say and the looping variance I is in between 1 and 6. And you can pretty much conclude right away. I know that I should be between 1 and 6. I also know that I should be strictly larger than 5. There's only one possible value. I should be 6. I should be 6, right? For this particular example, that's enough justification. But sometimes you may have to go a little bit deeper, depending on how complicated the Boolean expressions are. Okay, quick recap, and then we'll take a short break, right? So we talk about just the syntax for iterative algorithm. That one should be good. We got precondition, postcondition, and loop invariance. And we talk about the flow chart about checking it mechanically, right? Tracing it. And then we also talk about the general correctness condition. You got to make sure we exit from the loop. And also loop invariant has been maintained. That should entail, logically, the postcondition being satisfied. Right? So whenever you're kind of asked to argue about the correctness, you have to remember this proof obligation. Okay? Question?
Something a developer was just saying, like this postcondition is just like assert I as an integer, and then.
That's very good. That's very good. Yeah. So your fellow student basically is saying, I will make it even more extreme, right? What if I simply put assert true? That's kind of weakest predicate you can have. That means in some way, having this postcondition here, you basically have some algorithm that can never be incorrect because anything should imply true, logically, right? But that one there is not going to be very useful. You don't really have high confidence about what you can claim, even though you can prove something, but you don't have high confidence about what you're proving. That's why I said the correctness you have is with respect to the quality of your contracts. So in practice, you really want to make sure at the design phase, you want to make sure the pre and post condition are properly designed. You don't want to have any true or false extreme. You don't want to, right? We wouldn't dive too much into about how exactly you should really design. That'll be the job for other courses. Yeah, that's a good question. Or even more extreme. Let me give you another one. What if I can simply say assert false? That means I also have some very useless algorithm. That means any input the user passes, I'll just fail. That's also not very useful, right? You don't want to go for extreme. You want to give some balanced predicates. Yeah. All right. Let's take a short break, and we'll take attendance, and then we'll continue after the break to see how much we can go for. Now we kind of understand what loop invariant, precondition, postcondition. Let's see the tutorial exercise, right? You can look at the lecture site. Let's look at that very briefly, right? Of course, you can look at the PDF yourself too after the session. So we are now in tutorial 7 right here. If you look at the instruction here, right? Look at the question itself, right? It's not a complicated algorithm, right? Still something simple enough so we can practice about the concept, okay? All right, so this one here is about an iterative algorithm to find out the maximum in the input array, okay? But let's look at the question itself, okay, to see what we should do, right? So there are several questions over here, okay? So just to warm up, we can think about what should be the pre and post condition for the algorithm. What should be the input condition to be valid, and also what should be the expected output, right? Let's look at the pre and post condition first, right? It's going to require a little bit of some predicate, like a quantification, logical quantification to specify, okay? And then specifically, let's say you're proposed this particular loop invariance, let's say, right? We're going to look at that together, okay? This might be a possible question you might be given later. You might be proposed some loop invariance and you want to judge to see whether or not it is appropriate. Basically, it would be appropriate if, number one, it can be established. Number two, it can be maintained for all the iterations. If that's the case, then you would say that it is appropriate. Otherwise, if you don't think that's appropriate, you have to disprove it by giving some witness, like a scenario where the loop invariance will be violated, right? That's something we'll see, okay? And if you don't believe that it's appropriate, you can provide some fix to see what should be fixed. Maybe adding some more predicate or maybe fixing some boundary condition, right? Depends. And once we got the loop invariant fix and also precondition, postcondition, we got a complete contracts for the iterative algorithm. And then we can actually use that criterion, we talked about before the break, the not be and li, loop invariant, implies the postcondition, right? That's the one we spoke about before the break, right? So that's kind of the flow for this exercise here. That kind of just repeat about what we just said on that smaller example, right? Let's take a look at this, okay, together. hopefully we can at least cover 1 and 2, right? Hopefully, okay, we'll see. We got about half an hour. All right, let's start from this one here, okay? So we see that we got the precondition right here, and also we got the postcondition right here. So postcondition is right before we return the result, which is supposed to be the maximum value in the array, right? Let me just make some example array for you. Why don't we say we got array A, which is the input. A here, which will be the A here, and that's the input. So we have 20, 10, 40, and 30. Let's say, okay? And we got precondition and postcondition, we'll talk about it. And other than that, we also should get looping variance right here. Looping variance, whether or not it's established. Also the same looping variance, whether or not it's preserved or maintained at the end of each iteration. Everything else is more like a part of the algorithm, like a programming statements. So we got, for example, these 2 lines, nothing to do with the iteration itself, it's just to prepare, okay? So now you see some initialization that's not empty. So think about this part here is the init. Okay, so for these 2 programming statements, it will be statements init. Okay, and then for the body of the iteration, it will be right here. This part here, this part here, this part here, and right here. Right, so that'll be the body of the loop. The statements for the body of the loop. And we also got the state condition. Right? So this part here is the B that we spoke about. Right? Right, so that's basically satisfying the structure, for the algorithm that we spoke about. Any questions, any doubts about up to here? Seeing the correspondence, right? We're okay, right? Okay, let's do something simple just to make sure we understand input and output, right? In order for us to find the maximum for an array, what should be the precondition? Diego?
I believe it shouldn't be empty.
Shouldn't be empty? Yeah, because in that way, you don't really know what the maximum is, right? Because in order for you to find the maximum, that maximum must be in the array. But if the array is simply empty, nothing you can find. Right? I agree. That's good. Should be straightforward. So here, you can simply say the precondition. But of course, if you like, you can say, number 1, A should not be null. And also, A dot length should be larger than 0. But if you like, if you say not equal to 0, that's fine too. Right? Just not empty. All right, that's precondition. That's easy. Good. How about postcondition? So here, I'm going to make our exercise a little bit easier, a little bit simpler. Okay, first of all, for example, the maximum in this array is 40. I got to make sure whatever maximum I figure out from the array, it's got to be something existing in the array. For example, I cannot just give you 70. That's big value, but it's not even in the array. So it cannot be the maximum in this particular array. I got to make sure whatever result I return, it must be a member of the array, right? So that'll be condition number 1, okay? So you can think about R1 is the result exists in A, all right? This definitely is very informal. Exercise for you. How do you express this informal constraint here formally using predicate? Oh, you want to say something? Yeah, go ahead. Yeah. Okay, okay, it's getting closer. Okay, now that you mentioned, I should really discuss it, right? You're saying that there exists x in A and x equals result. I presume that's what you meant, right? Not exactly. I'll tell you why. This is an array. Array is not really a set. Array is more like a sequence, right? It's like a sequence where you got indices, also you got like elements, right? So you're getting there, but not exactly, okay? But I can give you some feedback here, but once we talk about R2, you will see exactly how to specify this. I just want to give you some comments, okay? This one here, not exactly right. Instead, you want to quantify over the indices of the array. Could be maybe from 0 to up to a.length minus 1. Right? That one you can do. Once we see R2, you'll see exactly how that should look like. Very good. Good try. Okay. Okay, R1, you can do it. Let's now ignore R1, right? Let's talk about R2. What other post conditions should we impose for finding the maximum? In this case, the maximum will be 40. What is so special about 40? Forty is larger than or equal to the first element at index 0. 40 is also larger than or equal to the second element at index 1. 40 is also larger than or equal to itself at index 2, and etc. Right? Yeah, go ahead.
For some element x, where ax.
When you say for...
I'm trying to say that
yeah.
if you take 40 and subtract any element from the array, it'll be greater than 0, the result. And then
I
if
see.
one of them is equal to 0, then it's part of the array, and that also satisfies it.
Interesting. But I would say that might be a little bit more complicated than necessary. I know exactly what you mean, right? So when you say, for example, 40 minus 20, that one is larger than 0. But a simpler way of saying that is 40 is simply larger than or equal to 20, right? You don't need to say minus 20 will be larger than 0 or equal to 0. You don't need to, right? I totally see your point, right? Okay, good. So what we want to say is something like this, right? Let's go a little bit more from scratch, right? I think this tutorial we can afford some time to make it a little bit more spoon feeding. So this one here, so result should be larger than or equal to A at index 0. Result should be larger than or equal to A at index 1, right? We talk about A, 0, 1, 2, 3 in this particular example, okay? Also result larger than or equal to index 2, which is itself. That's okay. That's why it should be larger than or equal to. Should not be larger than. In which case, 1 cannot be larger than itself, right? Also, finally, result should be larger than or equal to A3. For this particular example, yes. However, the length of the array can be arbitrary. Can be 10, can be 20, can be 100. How can we generalize this? Well, we're going to use a logical quantifier, right? Like a for all. All right? All right? And I'm going to open another page, right? Just one moment. Think about the 0, 1, 2, 3 over here is exactly some universe of disclosure from index 0 all the way to a dot length minus 1. To make it general, we want to quantify over this universe of disclosure. Right? Let's do it again. Okay? And we'll figure it out. Okay? What we can do is like this. Oh, sorry. Right here. All right. Think about in general. If I got A, the input array, this is my input array. Starting from index 0, index 1, all the way to, some arbitrary index, could be I, for example, any one, like a random one. And the very last index should be a dot length minus 1. Okay? What we really want to express is the return result for maximum should be larger than or equal to each value, each elements in A. So now in this case, should we use which quantifier? For all will exist. For all, right? We're going to make sure this will hold for every element. Okay? You want to try? For all. Oh, you'll pass. Oh, sure. No problem. Diego, I know you want to volunteer. Go ahead.
Sure. Okay.
Oh, by the way, let's use the dummy variable j, because I is already a loop counter. We don't want to have any clash.
So the index will be A or I?
I say, how about we say j, if you don't mind. In my solution, it's j, so it'll be easier. Yeah.
Okay, so for all J,
For all j, okay.
such
Such that, go ahead.
that is bigger or equal than 0,
Okay, I like it. What should be upper bound?
A dot length minus 1.
Good. So there are two ways. Oh, yeah, sure. Yeah, absolutely. Yeah, there are two ways to write this. You can either say less than or equal to a dot length minus 1.
Or less than A dot length.
I agree. Absolutely. Let me write it down. Either way. Okay. And now, followed by this, should we put implication or implication, right? Good. Awesome.
So that implies that A of J, no,
A of j, right? Basically, we just choose any arbitrary, we just choose any arbitrary elements here. And the result must be larger than or equal to that.
okay, so that should be greater or equal than,
Yeah, I think maybe I should put it this way. You want to say the result?
oh, okay, yeah. I was
Yeah.
I was thinking-
We can say aj is less than or equal to result. It's equivalent, right? Okay.
And then result just corresponds to a particular
Element, yeah, exactly. So you can think about this one. This one's R2, right? So R1 will be for exercise. That's something you can try, okay? R1, okay? All right. Let me make a little bit more annotation for everybody, okay, quickly. And then we can move on to talking about looping variance as well. So over here, we're saying that if j value is within this range, then this must be true, right? It's implication, right? It's kind of like a conditional. Then this holds. All right, so that's a post condition. We're saying across the array, every element should be less than or equal to the maximum, right? Of course, if I simply change this one to be finding the minimum, you would just flip the relation, right? Any questions about this? Good, okay. And now we got a precondition and postcondition, right? Let me just say a little bit more about them in general, quickly. Okay, and then we'll look at one particular looping variant, and we'll judge together whether or not that one is good, appropriate. Okay, so just some general guidance about when you write the pre and post condition. Okay, so whenever you want to write a Q, which is a precondition, it's all about input validity, right? So you only want to refer to input values. In this case, you only refer to the parameters, right? Just A over here, right? Just input, okay? That's precondition. And when we talk about postcondition, this one here could be, for example, just array A. And postcondition might refer to the input, the array, and also the output, the return result. Right, you can see that the postcondition we figure out, it refers to A and also refers to the result, input and output. Right? So that's why I said in general, think about postcondition being a relation between the input and output. right? Okay. Now, loop invariance. That's going to be the fun part, right? Think about loop invariant. We'll try to explore some middle way between the pre and post condition, okay? Let's write it down, and then we'll look at one example, okay? Loop invariance. You can definitely refer to the input. You can definitely also refer to the output. Now, the third category is really tell you the essence about loop invariance. Loop invariant is going to be somehow checked at the end of every iteration. That means the loop invariant ought to monitor the intermediate values of some local variables or the output variables, okay? Typically, it could be the loop counter, or it could be other local variables. Simply because the philosophy about having loop invariant is these represent the intermediate progress of your loop of your iterative algorithm. Intermediate progress of the iterative algorithm between iterations, basically. Between iterations. All right, so just general guidance, okay? And let's now look at, rather than having you figure out from scratch, why don't we take a look at one proposed loop invariance, okay? Let's take a look at that. Okay, so we still have this algorithm here. I didn't change anything. And also we got the array. Let's keep the same input array. Let's say we got 20, 10, 40, and 30. Okay, the same. And let me propose the following loop invariance. In many cases, not necessarily in general, but in many cases, you can think about the loop invariant is more like a specialized version, or like a restricted version for the post condition. So the post condition tells us, given this array, the result must be larger than or equal to every element of the array. The loop invariant is going to go a little bit restricted to say, depending on what the loop counter value is, maybe I is around here. I want to make sure everything up to and including I over here have been somehow processed. So my maximum is the maximum with respect to this sub-area of the array. Anything beyond the loop counter, I don't care, right? So in this kind of a pattern here, once you figure out the post condition, you try to make a more restricted version, maybe about a universe of disclosure to figure out loop invariance. But let me show you, okay? Proposed loop invariance. All right, so this one here is going to refer to input, output, and loop counter, and also local variable like a result, everything, okay? For every j, j is in between 0 and, now in this case, rather than a.length minus 1, that's the ultimate outcome. But I want to say I'm only focusing on where I am after the current iteration. I. Right? That's a loop counter. Everything else, almost identical as before. That's the loop invariance. If you compare this loop invariant with the post condition, this is the only part that's different. All right? Yeah. Oh yeah, I'm only talking about R2 actually. So for now, we're only focusing on R2. Yeah, you're right. Yeah, R1 should be there too. Yeah. Okay, actually, I think really don't want your fellow student watching the video to also get confused. Only for R2, just for now. Let's imagine that this is a test question or exam question. I give you this proposed loop invariance. I would say, now judge whether or not it's appropriate. If it is appropriate, you can demonstrate, justify why it's appropriate. to make sure it can be established, it can also be maintained for all the iterations using this example. If it is not appropriate, tell me exactly when this loop invariant is going to fail unexpectedly. Can anybody kind of try to maybe trace very quickly in your mind? Don't worry if you cannot, don't worry. It's kind of tricky for the first time. I can tell you that this loop invariant here is not exactly right. It's going to fail at some point. Yeah, go ahead.
On the last step, J goes past the bounds of the array.
No, you're talking about go beyond the maximum index, right? No, not exactly. It's a little bit more sophisticated. Tian Tian?
We can't be sure that a at index I is less than or equal to result because we can increment I at the very last.
Yes, that's pretty good. Spot on. Exactly. I think what Tian Tian just said is like this. Okay, I'll point it out. Okay. You can see that here, when we do the processing here, we try to do, for example, if the current value is, for example, 2, let's say, right? So that means after this particular body of the loop, we only have handle up to and including index 2. But we're going to increment the value of I to 3. So here, when we check the looping invariance, we are using the value 3. But we haven't really handled when I is equal to 3. That's the job for the next iteration. So somehow this one here is not exactly right. We are really asserting an area that haven't really been covered just yet by the loop, abstractly. But guys, don't worry. That's a little bit more like an insightful observation. But let's now try to trace it to see exactly how, right? Okay. Let's see. Okay. So we talk about after certain iteration and the value of I, and also the result, also the loop invariance, whether or not it's actually true, and then we got the B, which is right here, right? Whether we should really exit from the loop. All right, let's talk about initialization. After this initialization over here, we know that I would just be 0. I would just be 0. And then the result would just be A at index I, which is 20. And then when you try to look at the looping variance over here, we're saying that for every J, J is in between 0 and also 0. 0 to 0. Basically, we're talking about this element here, right? And then the result, which is 20, larger than or equal to itself. True, right? Let me write it down, okay? Just in case you're still a bit struggling. That one there, we're saying for every J, 0 less than or equal to J, less than or equal to 0, because we got 0 right here. And then result larger than or equal to AJ. This part tells us J can only be 0. And if you replace this part here just by 0, result at the moment is 20. 20 larger than or equal to A at index 0, 20 itself. So it's true. All right, so it's established. All right. So this one here is established. And then if you try to check this condition here, A dot length is 4. 0 not equal to 4, true, right? So we should keep going. All right. Let's go for the first iteration, okay? Now, first iteration. After the first iteration, what's going to happen, right? So basically, we look at this part over here, right? So currently, I is simply equal to 0. Okay, so after the first iteration, okay, let me try to trace a little bit for you. All right. So think about here, A0 larger than the result, 20, right? We're basically just comparing A0 with itself. It's not larger than it, so we don't really update. The maximum remain to be 20, right? But we're going to increment I by 1, okay? Result remain to be 20, and I will be incremented to 1. Now, question here. You can see what's going on here. I has been incremented from 0 to 1. That means the looping variance is really asserting this sub-range of the array. However, we haven't really even processed this part over here. We haven't. But this 20 here that we got from the initialization happened to be larger than or equal to that. Happened to be. So we get away from that. Right? So now for this one here, I'll write it down. Okay? So think about this kind of tracing maybe after the session. Right? I want to mention the insight to you. So this one here will be maintain. However, let's now take a look at why it is maintained. For every j, 0 less than or equal to j, less than or equal to, so I value now is 1, right? 1 implies the result larger than or equal to a j, right? If you look at the range over here, what can be the possible values for j? 0 and 1. All right, very good. Okay, 0 and 1. So 0 and 1. And is it correct the result, which is still 20, larger than or equal to this element and this element? Indeed. So it's maintained somehow. Okay. So this also check. And if you look at the 1 here, 1 is not the length, right? So we still go on. All right. What's going to happen in the next iteration? Apparently, I is going to be somehow incremented from 1 to 2, right? First of all. And then, oh, sorry, just before that, okay? Of course, let me put it this way so you will see exactly. So when we get to this particular iteration, in the beginning, I would just be 1, and then it will be incremented to 2, okay? When it is equal to 1, we're basically going to compare 20 and also this value at index 1, right? So here we're going to have a at index 1, and the result currently is still 20, right? So 1 here is 10. 10 larger than 20 is false, right? So remain to be 20. All right, 20 here. And I will be incremented from 1 to 2. So now, can we somehow try to decide whether or not the looping variant now is going to be maintained still? Diego, you could have said no. How come?
Because I gets incremented to 2, and we haven't processed that, so now 20 is not targeted.
Yeah, exactly. Oh, good. Let's now see that. So here, it turns out this will be where we're going to see the looping variant violation. So for your explanation, you ought to point out this is where we're going to get looping variant violation. Let's write it down here. Okay. Looping variance violation. Okay. Star, star, star. All right, let's see why. At this point, I value is 2. Okay. For every j, 0 larger than or equal to j, larger than or equal to 2, which means we're going to look at this portion of the array. But so far, we have only covered this part, only. Right? We haven't really covered this part just yet. All right? That implies the result larger than or equal to A, J. Okay? Let's see how this predicate can actually fail. Okay? So J value can be either 0 or 1 or 2, right? Can be 20, can be 10, and also can be 40. The result at this point is still 20. We are really asking, is 20 larger than or equal to 20? Yes. 20 larger than or equal to 10? But 20 larger than or equal to 40? No. This is where the violation occurs, right? That's something you guys ought to point out and explain, okay? Okay, so this part here, false. Because A result larger than or equal to A at index 2 is false. And the result right now is 20. A at index 2 is 40, right? It's not the case. So the big picture, of course, you ought to really trace this one by yourself and see exactly how violation might occur. Okay, so here's the thing. Whenever you're given this looping variant over here, to really see if that's really appropriate, you got to make sure you check it, number one, after initialization. In this case, it passes, which is good. And then for every iteration for that example, either you pick it, or I can pick one example for you. Give me 1 minute, okay? We'll be done. And then at the end of each iteration, you're going to evaluate the looping variant. And if you're able to go to the end of the algorithm and then everything actually just work, you can say looping variant is appropriate, right? Because eventually you can establish that post condition. If any part of the iteration actually failed, you got to stop it and say, here we got violation for the looping variance, right? A little bit tricky, but it's not too hard, right? Try to go over this maybe over the weekend before Monday's class, and then we're going to apply this kind of understanding and apply it to Dijkstra. All right, okay, I'll see you guys next week.